This segment we're going to talk about isentropic efficiencies, and isentropic efficiencies allow us to compare the isentropic or the ideal case to the non-isentropic case. So that ideal case, that's our isentropic process, and an isentropic process is adiabatic and reversible. So adiabatic meaning that the only energy crossing the boundary is in the form of work, usable work, not heat transfer. So if you do have usable work, this is a good thing. Or if your device is intended to produce work or consume work, that's a good thing. And reversible, meaning that you don't have any friction or anything like that in your system that you have to worry about. Remember that it is impossible to have a truly isentropic process. We can kind of get close, but you can't get there 100%. The actual process is, of course, the non-isentropic case. So you have irreversibilities in there, you may have heat transfer, but you do tend to try to minimize both of those things. And isentropic efficiency, it's expressed as a percentage. So if it's 100%, that just means you have an isentropic process. So let's talk about turbine isentropic efficiency. So it's defined as the actual work over the isentropic work. So the actual work is the work output for the actual process as you expand from P1 to P2. And if I apply the first law, I can get an expression for that. So I've got an open system, and when I make the appropriate assumptions, the ones that I typically do for a turbine, I'm left with H1 minus H2. And then that WS, that's the work for the isentropic process, the work that you get out of the expansion process from P1 to P2. So the P1 and P2, that's how it's defined. It's defined, this isentropic efficiency is defined between those two pressures. So if I apply my first law, I get sort of the same thing, but I'm going to put a little S subscript beside the W and the H2, just for housekeeping purposes to distinguish between the non-isentropic process and the isentropic one. So that H2S, I put a little S right there because it's the enthalpy at the end of the isentropic process. I don't put it at H1 because H1 is my initial starting point. That's where I'm starting from. So it's going to be the same whether I'm talking about going through an isentropic process or whether I'm going through a non-isentropic process. So let's look at this a little bit more in detail. So sometimes you might get confused about, because when we talk about these isentropic efficiencies, you'll see sometimes the isentropic term is on the top. So why is it on the bottom in this case? Well, you want the term, the bigger term, to be on the bottom. And for a turbine, it's supposed to give you work. And that's a good thing. That's the ideal case. So ideally, you get a lot of work out of it, but in reality, you're going to get a little bit less because you've got things like friction within your components to overcome. So if I look at the actual process, and I'm looking at it on a HS diagram, and the trend lines for this are, we're not going to work too much with HS diagrams. It's really just to kind of visualize the process here. So don't worry about having to draw things on an HS diagram. But if we're looking at the work for the actual process, you're looking at the difference between H1 and H2. So you're out there in the superheated region and you expand, your enthalpy goes down. And for the actual process, it goes down just to state 2. But then if I expanded it isentropically, then it would go all the way down to H2S. So I would harness even more energy out of that system as it goes from P1 to P2. So the work for the isentropic process is bigger. And that's a good thing because bigger work output makes bigger profit, right? All right. Sometimes people get a bit confused about, all right, so I'm comparing the actual process to the isentropic process. And I know that state 2 and state 2S are not actually the same, but are all the properties different, or are just some of the properties different? Well, P2 at the end of the actual process and the non-isentropic process are the exact same because that isentropic efficiency is defined between two given pressures, P1 and P2. So it's the same for both processes. But all the other properties are going to change. So when you calculate, if you calculate the temperature, the enthalpy, and the quality for the isentropic process, you need to go back and use your isentropic efficiency to figure it out for the actual process. And we'll work some problems dealing with that so you get a feel for what that means. All right, now let's talk about a compressor and a pump. So we're talking about compressors and pumps, not like a piston cylinder arrangement, but we're talking about open system type compressors and pumps. And the isentropic efficiency, it's defined exactly the same. You get the isentropic work over the actual work. So you'll notice it's flipped from the turbine. So the isentropic work is on top. So the work, the actual work, that's the work required for the actual process going from P1 to P2. So if I apply my first law, it's got an open system. I apply all the appropriate assumptions, got things in terms of H1 and H2. And then if I look at the work required for the isentropic process between those two pressures, I get the same thing, except I want to make sure that I put a little S beside the work term and the enthalpy at the end of that isentropic process to differentiate from the actual process. All right, so once again, why is the isentropic work on the top and the actual work on the bottom? Well, a pump requires work. And ideally, you wouldn't have to put in a whole bunch of work. So that would be the term on the top. Ideally, that would be small. But in reality, you got things like friction that you got to overcome. And so it's going to make that term bigger. And that's going to be the one that's on the bottom. So for the non-isentropic process, so you're going from state 1 to state 2. And so that's on that HS diagram. And you can see that H2 is higher than H2S. So if it's an isentropic process from P1 to P2, you have to put in less work to get there. All right. And that's, it'd be better if you don't have to put in as much work. Less work equals less cost to you. All right. So we've got, we applied our first law. So we've got an expression for isentropic efficiency. And once again, when you're looking at the thermodynamic properties at the end of that isentropic process as compared to the actual process, the pressure, P2, is the same for both of them, but every single other one, they're going to be different. And you'll probably have to calculate what they are, what the temperature, the enthalpy, the quality, what those are at the end of the isentropic process, then use your isentropic efficiency to figure it out for the actual process. All right, isentropic nozzle efficiency, that's our last device. So this is a little bit different. A nozzle, you're trying to speed things up. So what we're going to do is we're going to compare the kinetic energy at the end of an actual process to the end of the ideally isentropic process. So the first term, the actual kinetic energy, that's the kinetic energy at the nozzle exit for the actual process going between two given pressures, P1 and P2. So if I applied my first law and I made all the assumptions that I typically do, and for a nozzle, I'm going to go ahead and approximate the velocity at the inlet as 0, just because the kinetic energy at the inlet is going to be much, much less than the kinetic energy at the outlet. So if I do that, I get an expression in terms of enthalpies. If I do the same thing for the work or for the kinetic energy at the exit for an isentropic process, I could do the same thing, and I would just need to put a little subscript for the kinetic energy term and a subscript for the enthalpy at the end of that isentropic process. So let's see, here we go. All right, so if I look at an HS diagram, I can see that at the end of that non-isentropic process, the kinetic energy is going to be a lot lower. So as I go from state 1 and then I go to state 2, state 2 is going to be higher than H2S. So the kinetic energy at the end of the isentropic process is going to be higher. And that makes sense, right? Because if it's an isentropic process, you don't have any friction or anything slowing down your flow. Alrighty, and once again, that isentropic efficiency, it's defined between two given pressures. So the pressure P2 is going to be the same regardless, but when you look at the other thermodynamic properties, those are going to change depending on whether or not you have an isentropic or a non-isentropic process. All right, well, we will work lots of problems with this to get a good handle on it. Thank you for watching, and let me know if you have any questions.